Okay, thanks, Bevan. Good afternoon, everyone. My name is Billy Putnam. I'm an assistant professor here in the EC department. And I'm very excited to introduce our next event today, the Faculty Research and Grants Highlight Session. So in this session, the 5 faculty listed here are going to tell us about their vibrant research programs and some of the exciting projects their students and research teams are working on. Each faculty member will give an approximately 5 to 8 minute talk. And after each talk, we'll have about 2 minutes for questions. So if you have any questions, please put them in the Q&A box and I'll read them out to everyone. Okay, so without further ado, let's go ahead and get started. Our first speaker is going to be Professor Marina Radulaski, who's going to tell us about her exciting work in quantum photonics. So Marina, maybe you can take it away.
Yes, thank you, Billy, for the introduction. Let me share screen and ask the typical question. Do you see my screen? Yeah, good. Great, thank you. Hi, everyone. My name is Marina Radulaski, and I am an assistant professor at ECE. My research is in quantum nanophotonics, and my group is developing the next generation of quantum information hardware. Our vision has been supported by NSF, One Quantum, and Google Research. And today I'll tell you a bit more about those projects. The research we do is focused on using quantum emitters in semiconductors called color centers to build quantum information hardware. Color centers are defects in a lattice of a semiconductor, which means an atom is missing or some other atom is in the place of the original atom. And these defects, if they're in a wide band gap material, such as silicon carbide or diamond, they act as quasi-atoms. That means that they emit quantum light, which we need for quantum networking, quantum internet. And they also have a spin, electron spin, that can be used to store quantum information as a qubit. Now, they also have a pretty long coherence time, which means they can store quantum information for a long time. All these great properties become even better when the color centers are integrated with photonic devices. And this is what we specialize in. And the integration is either with a passive photonics, such as these nanopillars, or active photonics, such as these resonators. And across all the different applications of quantum information, silicon carbide color centers can really support the backbone of quantum technology. Here we are looking at 4 different sets of applications. So the first one is quantum sensing, where we integrate color centers with passive devices, quantum internet or quantum communication, where we integrate color centers with active devices, such as photonic crystal cavities. This route also is suitable for quantum computing, a new generation of quantum computers that use measurement-based quantum computing. And finally, analog quantum simulators, where we can use coupled cavity arrays with color centers to simulate phase transitions of superconductors. Now, interesting geometry that we use here is this triangular geometry. When it comes to waveguide and photonic crystal cavities and other photonic devices, they're usually in rectangular geometry, but there are some very specific nanofabrication challenges in terms of making such devices with color centers, where they have too much strain or lose their properties. And so NSF has funded us to explore this exotic geometry, the triangular geometry, as well as to develop fabrication methods that can produce such devices. And that led to a series of publications. The most recent one came in Nature Materials recently, where we modeled that triangular waveguides can emit light into a single mode, and also characterize the color centers that were fabricated in these triangular devices. And it turns out that they do not lose their properties. The coherence times of the spins, so the potential to store quantum information, are as long as before, of the order of a millisecond, which in quantum terms is very long time. And the optical properties are also very stable. We don't see any dancing of an emission line across the spectrum throughout an hour of acquisition. This is a result of an international collaboration with groups in Germany, Sweden, and Japan. Now, another project that was recently funded by Google Research uses currently available quantum computers like those that Google, IBM, and other companies have. So those are based on superconducting qubits to use these quantum systems to simulate quantum effects in our optical systems. So basically, we are mapping our problems that we usually use classical computers to solve onto a quantum computer to gain more insight, and then use that insight to improve our devices. In our most recent result in this area, which is also a collaboration with a group in Switzerland, we have coupled, or we rather have mapped the dynamics of a resonator with N atoms, and most importantly, a lossy one, a realistic case where the photons are being lost to the environment. And those are really hard to simulate. So typically we simulate them in exponential space and time, like this red line, on a classical computer. And so now with some mathematical tricks, with some quantum information tricks, we are able to map that in linear space and time, like this blue line, or zoom in to it, on a quantum computer. And we've executed it on IBM quantum computers, and we see a very nice match to the expected results. And so with that, these were some snapshots from our research progress in developing quantum nanophotonic devices for next generation quantum information hardware. And now I'd like to focus on the people who do this. So when I started my group 3 years ago, this was our core team, 2 graduate students, 2 PhD students, and 1 undergrad. And then during the pandemic, we had undergrad, PhD, undergrad, master, and so on students join and get experience in this new growing area of quantum information processing. And so our first 3 undergrads have graduated and went on either to prestigious master programs or got a quantum job. So this training really produces new opportunities for ECE students to take part in this growing and exciting area of new type of computing. So with that, I would like to thank you for your attention. And if you would like to reach out, my coordinates are at the bottom of the screen.
Terrific. Thanks for the great talk, Marina. Does anyone have any questions for Marina? Well, maybe I'll go ahead and get started. So it looks like you have a bunch of undergrads that are working with you. I've seen this in the lab as well. And it seems like they get a lot of great training working with you in the lab. But can you tell us a little bit about the opportunities you provide for them beyond the lab, maybe in courses that you teach?
Yeah, we have introduced 2 new courses, undergrad course in quantum computing and graduate course in quantum information technologies. And actually, half of my students have come through that way. So they get formal training in the class, and then they get hands-on research training in my lab. Those who have been in the lab for 2 or more quarters all have a publication. So they really get to see what it means to do research, and whether they decide to do that in academia or in industry, or decide that that's not for them, we're very happy to provide them with the opportunity.
Great. Well, cool. Well, thanks for sharing this all with us. This was really exciting. Okay, our next speaker is going to be Professor Sebastian Diaz, who's going to tell us about some projects he's working on involving terahertz and infrared sources that are based on Cherenkov radiation in hyperbolic materials. So go ahead, Sebastian.
Yeah. Thank you so much. Can you see my screen?
Yeah.
All right. Okay. Thank you very much for the nice introduction. So I'm going to talk today about recent work that we were just working about the generation of terahertz and infrared wave using Cherenkov radiation in hyperbolic media. And this is a collaboration that we have started between my group and the group of Professor Jos Hyatt. And first of all, I would like to acknowledge the CAF Foundation because we just got very nice support from them in order to realize our vision of the future of this technology, and also UC Davis because they also provided matching funds in order to complement this proposal. So as I was saying, our team, in order to work on this project, is myself, and in my research group, we work with applied electromagnetics. We try to control and tame light at the nanoscale, and we are focused on metamaterial and metasurfaces across the terahertz, infrared, and even microwave regions. And we focus on several new materials like graphene and hyperbolic media. And we are collaborating with the group of Professor Hyatt. And in his group, they are exploring electronic transport. They are working with 2D and organic materials, They have a lot of expertise on spectroscopy and also on hybrid electronic metamaterials. And I would also like to highlight our student, Juan, that he has been with us for a couple of years, and he has developed a lot of preliminary results of all of these projects that we have been working on. So to give you an overview on the idea behind this project is like there are like several ways that we as a society have in order to control and generate, in particular, general light. Like we have thermal radiation, we have lasers, we have LEDs, we have other approaches, but maybe one that has not been exploited so far for this particular application is Cherenkov radiation. So if you remember from your old days studying physics, Cherenkov radiation occurs when you have an electron that acquires a lot of energy, for instance, in a nuclear reactor, and escape. And for instance, if you have a swimming pool, a lot of water surrounding the electron, and the electron goes very, very fast, and it goes faster than the speed of light in that medium, is going to emit a photon. So this is the common blue glow that you can see in the pools in close to a nuclear reactor, like the one that we have here at Davis. So in this project, our goal is to take advantage of this type of radiation, but not for nuclear applications, but to control and generate light at terahertz and infrared. So our main goal is to create or generate the basis of a new solid state platform to generate terahertz and infrared light. How are we going to do that? Well, like a very brief overview, we are going to have a platform in which electrons are going to be flowing between these gold metals, and we're going to be using graphene. We're going to be using graphene or this type of 2D materials because they are very conductive. They provide the electrons can have a very large speed, and also they are plasmonic at terahertz and infrared, and we can control their properties. Our next step is to engineer and to tame at the nanoscale what are going to be the properties that surround the flowing electrons. And in particular, we are interested in engineering those properties to construct what are so-called hyperbolic media. These hyperbolic media offer a lot of local density of state in such a way that the electrons flowing in the media can couple through a Cherenkov radiation process to those states and generate a photon. Those media are really interesting, these hyperbolic media, because they relaxes the conditions in which Cherenkov radiation take place, and we can have that process with very low energy. So we don't need to have an electron with very high energy as happening in a nuclear reactor. We can generate this process in a portable and miniaturized device where the electrons are flowing in the structure. And finally, we're going to couple the energy. So this configuration, we are targeting the terahertz gap, in which usually lies between the electronics, where it is very well developed for smartphone, radars, microwave, and the realm of photonics, where we have infrared resistant, LCDs, X-rays, and the terahertz gap lies in between. And right now, society cannot take advantage of this frequency region because there is a lack of terahertz and infrared generators. And this is where we are trying to tackle and to develop our technology. So if we go around and we take a look to the current sources, and we have here the output power, and this is the frequency, there are like a very nice set of generators that coming from electronics that they go very well up to around 1 terahertz of frequency. And there are also a variety of lasers that have a very large output power up to around 10 terahertz. And in this region, there are some technologies, but all of them, they have significant drawbacks. They require very large magnet. They require, for instance, in differential frequency generation, lasers that are very well, they have to be very well synchronized in a nonlinear material, or they operate a cryogenic responses. So our goal is to use and to generate this drift bias hyperbolic media as a new platform to fill this gap. And while we're doing that, if we are successful, we are gonna hopefully this technology can have a large impact on society in terms of security, screening, spectroscopy, biomedicine, imaging. Like it's gonna open a lot of possibilities, and also in terms of terahertz communications, that increase of data rates, enable inter or intra-satellite links, or with the chips or plasmonic transceiver. There are so many possibilities that we we can do. So this is like a pretty new project. We just started working on that. We already developed all of the theory. That was our background, and now we're working experimentally to demonstrate this coupling. And then we're going to assess and manipulate the properties of this coupling, controlling the properties of the nanostructure to manipulate the bandwidth, the operation, and the efficiency of this coupling. And at the end of this project, we are going to apply this technology to demonstrate efficient broadband and miniaturized sources and to assess the application in several other applications. And I'm going to go very quickly, just one slide, try to explain the fundamental of this new operation principle. So here we have the energy and momentum of the electrons. They are drifting electrons, and we want this electron to relax and to emit a photon. And what happens is like the mediums surrounding the material are usually, they offer a very low density of states. So this process, like matching energy and momentum, cannot happen. And usually it's very narrow and not efficient. So the idea of using nanostructured material that they exhibit a hyperbolic response is like we can boost the coupling between the electrons and the photons and have sources that they can be broadband, efficient, and conform the basis of a new platform to generate light. And we start working on our experimental setup. And here at UC Davis, we have the Center for Nano and Micro Manufacturing, which comes with all of the state-of-the-art fabrication tools that we need to develop our structures. And we also have plenty of systems to characterize our devices in terms of FTIR with microscope, terahertz systems, cryostat to do temperature-dependent measurements. And we are also acquiring a scanning near-field optical microscopy setup, where we are going to be able to do measurements up to 10 nanometer resolution and increase the capabilities of UC Davis in terms of terahertz and infrared responses. So with that, I will just to summarize about this new project that we are very excited to work with. We want to fill this gap. We want to develop our drift bias hyperbolic media and to create and demonstrate the basis of a new solid-state sources for terahertz and infrared and generate light in terms of plane wave, surface plasmons that can be efficient, broadband tunable, scalable, miniaturized, and integrated and CMOS compatible. And hopefully we can have a significant impact in terms of applications and also connection with other fields. So that's all on my side. Thank you very much for your attention. And if you have any question about this project or any other activity that we're working in our lab, please feel free to reach out to me or to Professor Hyman. Okay, thank you so much.
All right, thanks for sharing the details of this really exciting project with us. Just a reminder, if anyone has any questions, you can put them in the Q&A box and we can share them with the speaker. Maybe for questions, I could just get started with one. So these hyperbolic materials are really interesting. Can you tell us a little more about how you make these?
Yes, just give me a second. Yes, so in order to, maybe I can just go to the very beginning of the slide. So basically what we are doing, here we can see this slide. So we are nanostructuring the material. So we are stacking a dielectric and graphene in a stacks with 10 nanometer resolution, or we are nanostructuring a graphene layer, again, with ribbons that are very, very small. So if we think like an RF engineer, we are just having a resonance between a dielectric and a metal, which is the same as having as a resonance between a capacitor and an inductor. And we are just trying to enforce that resonance to be very broad over a large frequency band. So the way that we can see that is like this dielectric is going to be a capacitor, the metal is going to be an inductor, and we engineer those to have this broadband resonance. And that facilitates the coupling with the electrons, and hopefully this is going to create the basis of a new platform to generate light.
Cool. Okay, we also have another question here in the chat. What is the time dependence of the terahertz emission that you're hoping to generate? Is it going to be pulsed or continuous wave, DC?
So initially it's gonna be like continuous wave. It's gonna be broadband. It's not gonna be like a continuous. The emission is not gonna be in a single frequency. This is gonna be like a broadband source. And we are actually exploring in our experiments. We are planning to consider both, like having a continuous emission and also doing a pulse. By simply controlling how are we drift bias these sources, we can control how the emission is gonna come out. So in that way, we can also transmit with pulses. So we are actually very excited and looking forward to our first set of experiments.
Cool. Oh, okay. One more question before we wrap up with you. We're all looking forward to your experiments. So what kind of powers can we expect to get from your device?
Right now, we are looking our quantum mechanics analysis in terms of efficiency. We are looking into 0.05 up to 5% of efficiency, which in this frequency range is pretty good compared to other terahertz or far infrared sources. And we are looking into the mid milliwatts range of power, which could be really significant.
Great, terrific. Well, thanks again for sharing. We'll maybe have you back in a year, and you'll show us some results of milliwatts of terahertz from your devices.
Hopefully. Thank you so much.
Okay, so our next speaker is going to be Professor Neville Luhmann, who's going to share with us some slides on the Davis microwave, millimeter wave, and plasma diagnostics group. Professor Luhmann, are you with us? There we go.
Indeed. Let's see. Okay, you should be able to see my slides, correct?
Cannot see your slides yet.
Let's try that one more time here. How about this time?
Yep, we can see them now. Great.
Okay. So our group develops technologies and applies them for a variety of applications, from diagnostics of high temperature fusion plasmas to imaging buried landmines in semi-arid environments, satellite downlinks. And in recent years, there have been two technology advances which have really been game changers for us. One has been micro and nano fabricated vacuum electronic devices. I'll show you a few examples, one of which that we're doing in collaboration with a small company called LV Speed, is a E-band 70-something gigahertz satellite downlink designed to produce about 50 watts. And to show you sort of the sizes, here's an iPhone 13 Pro, and it's a little over 14 centimeters. This is a little less than 14 centimeters. And this is actually deceiving because this is 4 centimeters and this is almost double that. The other technology that has really impacted what we do is millimeter wave ICs moving into what are often called systems on chip. Here's a W-band 75 to 110 gigahertz chip. It's a little over a millimeter in a side, and it's got the low noise amplifier in the beginning, the balanced mixer. It has the local oscillator multiplier chain and the IF amplifiers. So what I'll spend quite a bit of time on in this 5 minutes is the use these in millimeter wave and terahertz imaging for high temperature fusion plasmas. And looking at the chip technology, this little chip is a complete W-band receiver. It's mounted on a board sitting inside a split horn waveguide module, which does a number of things, including providing shielding. We stack numbers of them up for this particular imaging system where we image electron temperature and electron temperature fluctuations at the so-called D3D tokamak in San Diego at General Atomics. So in this embodiment, this is a passive radiometric imaging system, and this is the field of view. We have optics, so we can move that around. And here is a 160 pixel image, and this is crucial for understanding confinement, worrying about things like disruptions, and looking ahead at control. So here's the chip sits inside there. Whoops, I got carried away. I didn't want to go over. So this has made a big difference. System sensitivity, depending upon what embodiment, we've had anywhere from 10 to 35 dB worth of conversion gain. This is suppressed noise and provided real integration. So we've done a number of chips, miniature transmitters at V-band, receivers at B-band, F-band. And what we're working on right now is wide bandgap material using HRL's process, because these are definitely harsh environments. Applications are many: radar reflectometers, collective scattering, interferometry. And so now let's switch to the vacuum electronics. And we require high current density electron beams. And they say we're pushing these into the terahertz region. So the beam cross section is small. To get the power, we need high current, and we have developed so-called tungsten scandate nanocomposite materials that produce well over an order of magnitude increase in the state of the art for thermionic emission. So you need an electron source, an electron gun. You then need a way to focus and transmit the beam. Here's a magnet focusing system, and the beam needs to propagate through a interaction structure, and we've developed a number of them. A double staggered grating structure where a sheet beam passes through that, folded waveguide so that you slow the effective propagation, so that velocity, so that it's comparable to the electron beam velocity, double corrugated waveguide. And we've done a number of things. For DARPA, we developed a 50-watt, very wide bandwidth TWT for wide bandwidth communications and information transmittal with SLAC, Stanford Linear Accelerator Center, a W-band low voltage sheet beam klystron for plasma diagnostics, a 346 gigahertz backward wave oscillator, in collaboration with Beijing Vacuum Electron Research Institute, and my colleague David Britt in chemistry, a 263 gigahertz source for electron paramagnetic resonance system, and E-band sheet TWB and TWT. So we collaborate all around the world, and as far as the fusion plasma devices for millimeter wave imaging, we've essentially designed, fabricated, and implemented and commissioned essentially every one of these devices around the world. US, in Germany, in China, a number of them, Korea, and Japan. Where do the students go? All over the place. Government, academia, industry. There's a little snapshot of our group. There's lots of opportunities coming up, as I said, not just in the fusion plasma diagnostics, but all sorts of other applications. Thank you.
Hey, thanks for sharing all these exciting results with us. Maybe I have one question. For the vacuum electronic devices, the interaction structures you showed, they look like they're all metal, and they must be pretty small to operate at these frequencies. I was wondering if you can share with us how your group actually fabricates these.
Yes, we've done it several different ways. Let's just see if I can go back. We have so-called nano CNC machining capability, where we can make very small structures. And the other thing that you skipped over is equally important is smooth structures. We need to get things that are smooth to less than about the 10 nanometer scale. If you want to look at skin depths at, say, at terahertz or so. So we have that capability. So these are actually made with our nano CNC device or devices. We have also, over the years, used LIGA, a lithographic approach for making these, but it's definitely challenging when you get down to these scales. What I should say is probably the most difficult when it comes to sheet beam devices. They are harder to focus with magnetic fields. And when you get down to the size of magnets that are required, say at 263 gigahertz, you do much better with round beams. With sheet beams, it's tough, and we had serious problems. Magnet vendors just couldn't deliver what they promised, and someday that really needs to be a research project all by itself. I don't know if this has answered the question.
Yeah, thank you. Well, terrific. Well, thanks again for sharing this exciting work with us. Okay, so our next speaker is going to be Professor Homayoun, who's going to tell us about his group's work in accelerated, secure, and energy-efficient computing.
Okay, great. Thank you so much for moderating this session. So everyone see my screen?
Yeah,
okay,
we can do
it. Okay. Hello, everyone. My name is Homayoun, and I'm associate professor in the department. And we are doing research in the area of computer hardware security. and what I would like to call it as hardware cybersecurity. In particular, we are focusing on developing solutions to address security vulnerabilities in existing system, legacy architecture, and also a future type of application. So first, let me introduce the lab and lab member and acknowledge the excellent work of the students in the lab. The lab is Accelerated Secure and Energy Efficient Computing, or ASIC, lab in abbreviation. We have a relatively large team of about 12 PhD students, 3 postdocs, and several master students that are working in a different area to address security across the design stacks. The 4 areas that I highlighted here are one is hardware security, reverse engineering, which I'm going to talk about it shortly. That is important for companies to protect their assets, their preparatory information when they send it to manufacturer to fabricate it, or after the fact in the deployment, not just for military application, but also for commercial applications, such as the company like Mobileye that was acquired by Intel. Their neural network engine need to be protected. It's their trade secret, so they don't want people to reverse engineering it. We have another group that are focusing on addressing the problem I call as AI for security and security of AI. And this is an interesting problem, that how we can use AI to address security vulnerabilities. It's a difficult problem to trust AI, first of all, and also how we can address the security and privacy and trust in the AI itself. So we have students that are working on this, and also we are looking at firmware security. I'm going to also talk about it briefly today, and we had some major work in this area published recently, and we are hoping to release also a tool to the community that can be used for research and also for even industry level deployment. Also, we are working on the area of architecture and system security, understanding the vulnerabilities of systems, looking at NIST CVE vulnerabilities in file system, in the architecture. Many attacks also recently reported, like Meltdown and Spectre. These are more architecture level attacks. They're trying to understand them better to find out how we can prevent these type of vulnerabilities to appear in future type of architecture design. The lab has been really successful in producing in the human resource training and producing a good quality researcher, engineer for the industry. These are the list of students graduated in recent years, and several of them landed in industry, academia, working in the area of the general area of hardware and cybersecurity. One of the main areas that we're focusing on is the IC supply chain and understanding what are the risk vulnerabilities in IC supply chain and how we can address it. So here in this figure, I'm showing a pipeline of a standard IC design flow that we start from the design of the IC, the IC design house. We can use multiple vendor also IP to integrate. We do RTL design, RTL verification, logic synthesis, gate level netlist, all the way to physical design, producing the GDS2 and then sending the GDS2 to the foundry for fabrication, the wafer design, and then the test and assembly and packaging, and finally system integration. The fact that these steps are not done in one location, they're geographically distributed across the globe, is a challenge because they're done in different locations, that they may not necessarily fall into the same jurisdiction as the main design house. And that is concerning. And with all of these design or entity, essentially, we need to share the entire design or major part of it. So that essentially could be a potential exposure risk, especially to companies that they want to protect their asset, trade secret, and so on and so forth. Many problems also could happen. Several entities can clone the design, can copy the design, can counterfeit, and many other that is currently a problem. So few challenges that here I highlighted are hardware Trojan insertion, that the Trojan can be inserted into the hardware. There has been a lot of report in the federal government, news, and DARPA had many programs, actually still ongoing program to address this problem. And that could happen in foundry, third-party IP provider, and also SoC integrator. Also overproduction or IP theft can be happening in foundry and SoC integrator. reverse engineering, foundry, SoC integrator, package, as PCB assembly, test facility, and also finally counterfeiting. To address this problem, we've been working closely with the federal government and also companies. We, as a part of a 5 years project, we finally able to tape out and successfully tape out, test, and produce and provide the community with the result of a design, including a hardened RISC-V architecture, as well as a 128 neural network accelerator engine to show that how the hyperparameter in a neural network, an example of a Mobileye, now Intel, can be prevented to be reverse engineered, copied, counterfeit, and etc., as well as the side channel, addressing the side channel leakage problem there, as well as a RISC processor that it cannot be reverse engineered. And particularly for RISC is interesting because a lot of companies moving to build their own architecture for RISC, and we don't have a standard in this design. And many companies are claiming significant advantage over existing design given the new, given the open access RISC ISA. So protecting their design is very important for these companies, which could vary from small, medium to even large entities. Also, we are looking at other aspects of the supply chain beyond just IC design, including IC programming and what we call as firmware, for instance. PCB design and firmware also programming also are two parts that are subject to various types of attacks. And they're also part of supply chain, given that nowadays companies, they are outsourcing many part of the design, even part of the firmware design to third parties. The question is that how can we trust those third parties that they're going to deliver them a clean firmware, or they're not using a third-party libraries in the firmware that they are polluted with various type of vulnerabilities. We are also developing several tools in this aspect. In particular, one of our research, which is funded by Noise Foundation and also NSF National Science Foundation, we are looking into developing what we call as firmware auditor, a tool that can investigate and inspect dynamic behavior of the firmware and static behavior of the firmware to understand potential vulnerabilities in the third-party library, in various program that we use in the firmware, and so on and so forth. As part of this research, we also disclosed a new vulnerability to the community. We published a paper in recent NDSS conference, the premier conference in the field. We show that the IC power management unit for most of IoT devices can be easily manipulated to change the voltage that delivered to the sensor and result in a sensor producing some junk result. And that could be catastrophic for devices that are deployed in sensitive medical application or military application, and or even in other type of commercial application. We are also working with companies in Google Pixel team to develop software that can look at the existing malware and also upcoming malware in a mobile app. So in this case, we're developing a threat intelligence system for, in general, for IoT large platform. In particular, we're focusing at this point on Android devices. And the problem when you go and talk with this company that they like Google and Android, that they're running big market for apps, they do a very good job in auditing the app the first time that the developers submit the app to the Android market or Google market. But the problem really is when these apps are releasing frequent update, and for many applications like gaming, this is very frequent. And for those of you who are using gaming for fun, you notice that on a weekly basis you get a update essential notification, mostly for better monetization of the game. And that is a problem because Google and Apple and also other providers like Samsung, it is not an easy problem for them to monitor all these subsequent updates. So in this case, we are working with them to develop a tool that can collect the data that these applications are leaving at a hardware level, the traces, the computer architecture level traces, microarchitecture traces that we can collect with hardware monitoring knobs, register hardware at the on the ARM core. We combine them with the data that we're collecting at the upper level of abstraction, such as at the software level or at the application level, binary information, and even information about the call graph, data call graph, information flow graph of the application. When we combine all these data, we can form a using multimodal learning, we can develop a body of knowledge of what the running application is doing. And that is essentially going to help us to understand whether the running application is doing something fishy or whether it's doing there's some anomaly in the running application or not. But bringing this to the user side would essentially would help companies like Apple or Google to avoid or essentially to help them in terms of monitoring application after the first release, the subsequent update. Also in the interest of time, I'll focus on some of our other ongoing efforts as part of the National Science Foundation Industry University Cooperation Chess Center. And this is a center that UC Davis awarded about 2 years ago. And it essentially, we are a part of 6 university team. And we are working with industry and as well as federal government to address security and vulnerabilities in embedded system. And we have together all these universities, we have about 100 plus students that are students and postdoc that are trained, mostly focusing on the area of cybersecurity. So this is really a valuable pool of talents that companies can tap into, can recruit, can collaborate for research, and for summer internship and so on and so forth. Currently, we have 32 industry members that are defining project for us or contributing. They are giving grants to faculty. There are many benefits to join the Chess Center, including very low overhead. Chess also, as part of 2021, 2022, and 2023, very recently we got the news, we received congressional support as part of National Defense Authorization Act. And for this year, thanks to federal government that they're taking security, they give it high priority. The center received $6 million as a whole, just as a part of the congressional appropriation funding. And here are just several companies that are involved in the center. And with that said, I'll be happy to take any questions if there is any. Thank you.
Okay, thanks for the really nice talk. Maybe I'll just ask one quick question. So your center, how do you interact with industry? Do you have an advisory board, or how do you get these problems from industry to focus on?
Yeah, that's actually a good question, and especially for faculty in academia. It's a challenging managing time, interacting with industry, given that all other duties that we have. So we get a lot of support from NSF. NSF runs this program, IUCRC, and they provide some benefit for the industry to join in NSF, to join this center, rather than directly going and getting into contract with individual faculty, including very low overhead of 10%. So universities would participate in this, and we started recruiting industry members for about 3 years ago. Once companies see that other companies, they are part of the center, there's ongoing research, and we share research with industry. There are weekly meetings with industry members, and there's this pool of talent, PhD students, that every time they want to hire security expert, they like to all be participant in the center and contribute. So initially it was always challenging, like any other kind of a startup you start. But once the ball rolling and you see more people coming in, that I think attract more attention and would make it easier.
Great. Well, thanks again for sharing these slides with us. This was really interesting.
Thank you.
Okay, so let's go ahead and jump to our last speaker, Professor Anh-Vu Pham, who's going to tell us about the work going on in his microwave microsystems laboratory.
Thank you, Billy. Good afternoon. My name is Anh-Vu Pham. I'm professor in the ECE department. These are my PhD students who are involved in the project. So today I'm going to talk about 2 projects in my group. The first one is the development of wideband components with the ultimate goal of building an ultra-wideband radar system. As you can see in this example, it is a very wideband ground penetration radar system that my student have developed from the component level all the way to antennas and the whole system integration, including data collection, as well as the imaging algorithm. In this particular system, the key here is that the poles are software defined. With that, we also develop algorithm to do digital pre-distortion to shape the poles to improve the imaging capabilities. So this project has been going on for several years, and the final demonstration is seen in this video here, which is the scanning of the Kemper Hall sideway to get some image underground here. So the project has been recently renewed to allow us to build a much more lighter weight version of the system. In the previous system, you can see that we use a arbitrary waveform generator, which is fairly heavy. But in this renewed project, we're going to use a much smaller bandwidth arbitrary waveform generator, which is lighter. But we're going to develop nonlinear transmission line to shape the poles so that we can get a much narrow poles from a low speed AWG and build the entire radar system similar to the ground system that I just discussed. In the next project, which is a totally different topic, this project has been funded by Keysight Technology. We've been working on this project for several years. Our goal here is to develop very wide bandwidth components with very high power, relatively high power in terms of frequency. We started out with roughly about 90 gigahertz bandwidth a few years ago with about 100 milliwatt output power. And over the years, we have really improved the bandwidth performance of these amplifiers to 150 gigahertz to 170 gigahertz. Our latest results, we have some amplifiers now that are achieving almost 260 gigahertz bandwidth. And some of these components are coming back. And ultimately, our goal is to develop amplifier with more than 300 gigahertz bandwidth and frequency, as well as reasonably high output power. All right, thank you very much for your attention.
Thanks for sharing those slides. Maybe I can ask one quick question. So the results here for your indium phosphide integrated circuits, these seem really impressive. I was wondering, what do you think the ultimate limits of this technology are?
It's the limits are always within frequency and bandwidth, right? But there's some reports on some of the indium phosphide technology that can get up to 600 gigahertz, or higher in terms of frequency. But power going to be a key issue. And of course, in my group, we have developed a lot of techniques to really get more power out of the device. And there's several levels of doing power combining at the device level to the subsystem all the way to the system level. So hopefully, we can get both the high frequency performance as well as the high output power. That's going to be our goal.
Okay, so there's also one quick question here in the chat. So the question about the first system you showed, the first radar system, the question was whether the system is synchronized with some kind of singular master clock.
Oh, absolutely. All of these are going to be synchronized with a master clock for both the transmit and the receiver. And it's all software controlled.
Cool. Okay. Well, thank you again for sharing these exciting results. So I think this wraps up our research and grants highlight session. Thanks to all the speakers for sharing summaries of their research. A lot of exciting, diverse activities going on here at UC Davis. And I think that here I'll pass it over to our organizer, Jane Gu, to take us to the poster session. Jane?
Sure. Thank you, Billy. My name is Jen. I'm a professor at this department. I hope everyone enjoying the program as much as I am, including the very inspiring keynote speech very exciting research talks, as well as great viewpoints of the pandemic, how it could, already generate positive effects and also continue impacts on our life.